welcome everybody. First, a general thing. Simulation environments in computational neuroscience, such as Neuron, Nest, or Brian, they each provide many tools needed by the user to carry out high-quality simulation studies. And in these tools, models are described very differently, and the environments have specific features. That means that it's hard to move models between these environments, which means that if you want to build a larger simulation and reuse other people's work, then it's difficult to reuse them. What happens now? Okay. So as systems grow and encompass more subsystems, they rapidly become unwieldy to develop. So in general, software in computational neuroscience tends to have a monolithic structure. Software interfaces, for example, APIs, allow for use of different implementations of software components. Music is an API and an implementation in the form of a C++ library, which supports flowing of data between tools during simulation. If you look to the right of this picture, what you see is three different applications, A, B, and C. They are each, in this case, parallel applications, which can run on a supercomputer. But music, of course, also supports use on a laptop. And what you see on the sides of this application is a depiction of something called music ports. So if an application publishes one or more music ports, music allow these ports to be connected easily to each other. I'll go more in depth in that in a moment. So the use cases done for music is that you can build larger models by combining other models as components. And that means that you also can model multiple scales or combining different formalisms simultaneously. And the way you do this is that you run a co-simulation. That is, you can run different simulators specialized on these different formalisms and supporting different models. You can run them together and connect the axon, sort of crossing the boundary between simulators. So music contains a simple API for shipping spikes and other data in and out of a simulator. It has parallel and scalable algorithms, so you can run a larger model in a supercomputer. Concepts and algorithms for selecting neurons from a population for data streaming, independently of how they are distributed over processes. It has a scheduler which allows communication in loops, also nested loops, and it has Python bindings. So this is some background of what music is, but the plan for today is that I will first talk about some practical things about Docker, which you will use to run experiments in this tutorial. I will then give a short lecture of some of music's basic concepts, and then we will have this hands-on tutorial. And that will have 4 different sections. I will first show how C++ applications can use music, so you understand if you want to modify your own existing application to use music. I will show how music is typically used from within a simulator. I will show Python scripts that use music using the Python binding of music. And finally, I will show you the new Pine music interface, which allows you to create populations in different simulators from within Pine and then easily connect them to each other. And I also hope to show at last a demonstration of how music can also enable talking to neuromorphic hardware. Okay, so Docker. So a Docker image is an executable package of a piece of software that includes everything needed to run it. It's code, runtime, system tools, system libraries, and settings. When you start such an image, you have a running container of this image with its own file system. And this is the environment that you will run music in today. You can download the image with today's tutorial environment by doing docker pull mdjurfelt sim ebrains 22. So maybe I should, if I can, I should, or maybe Björn, could you put that in the chat so that we have it recorded for the session?
I cannot copy paste it, of course. I can only type it. But if you could cut and paste it into the chat.
Yeah, I can do that later. Let's see. Yeah, that was a bit stupid. Okay, so anyway, I'll continue now. So when the tutorial starts, I will try to get this into the chat if nobody else does it before me. Okay, so the first command there is how you retrieve the environment. It demands a rather large storage space, a little bit less than 1 gigabyte. And then you can launch the container and enter it using this other command. So this option -IT is just to get a terminal session in this environment. The name option, it should be 2 dashes before name, is to sort of name this container sim ebrains so that we can refer to it later. And then, so you get then a terminal session in the container, and you can exit it with typing Control-D, or exit, you can type that also.
Michael, one question.
Yeah.
This is now for running something locally.
Yes.
Will you show also things running on the eBrains research infrastructure platform so that we can also follow along something which does not require a local Docker, or is that required?
No, we will only run locally now. Yes.
Thank you.
Mm-hmm. Okay. And if you have exited this container, you can enter it again using docker start -e sim ebrains. And then something a bit complicated. I will paste this into the chat also. If you want to have an X11 session so that you can start X applications inside the container, it's possible, and this is how you do it. And also, you might have to make sure that you have sufficient privileges to use this X11 connection. And I put a script x11.sh inside the container, which helps you to get those privileges. But you should probably look at this script, what it does, because it might be that you mess up the privileges of your sort of main computer this way, and then you need to use a similar command to get it back to your own privileges. So only do that if you know what you're doing. Okay, so a few words on the tutorial environment. So you are an ordinary user in this environment called user and have the numerical UID 1000. It is possible to become root using sudo -i. There is a simple editor called Xile, which is a lightweight Emacs if you're accustomed to that. If you want some other editor, it's possible to install it using sudo apt-get install Emacs. The operating system is Debian Bullseye, and this environment already now contains Nest, Neuron, Pine, Music, and a few other packages. So, okay, so maybe we should actually take a break there, and I can try to paste this into the chat. Are there any questions?
Maybe an alternative would be if there's if you can provide the slides. If you're planning to provide the slides anyway, then we could put them directly into somewhere where people can look at things.
Sure. Yeah, I can do that.
So I could link that one from the agenda, and then it's there even after the end of the session, which may be useful.
Right. No, I could do that.
Depending on where you want to provide the slides.
So, Björn, do you have an upload link for that? Or should I put it in the... So where should I put the slides?
Just a moment, I'll create one, unless you have one ready anyway, but if not, then I'll just create one for you now. And internal link, no, sorry, takes a moment. So you should now have a link in the chat, Michael, to which you should be able to upload. All very ad hoc, but why not?
Yeah, I should have, of course, posted this before. Now let's see. It should take some time to download the Docker container, so it might not be. There's the chat. Okay. Okay.
So just that we know what's happening. You're uploading the slides?
Yeah, yeah, yes, and I'm trying to find them. I found them. Okay. So now it's uploaded to your folder. Yeah.
I'll then have a link in the agenda soon.
Very good.
So if people would like to check out the slides that Michael created and shared, you can either go to the agenda, online agenda, or find them directly here.
Okay, but while people are sort of setting up their environment, maybe I should commence now with going through some of the basic concepts of music. So I will then share my screen again. Okay, so there. And then we have okay. So let's say that we have a network simulation. So we have a simulator, and inside this simulator we have a few neuronal populations. The arrows here are depicting projections, that is bundles of actions between these neuronal populations. What you can do with music is that you can expose for example, the spiking activity of a neuronal population. You can also ship other kinds of data, but we'll talk about the spikes here mostly. And then sort of the application can publish this spiking data as a music output port. Then we can have a second simulator, and if this publishes a music input port, you sort of conceptually can imagine this input port as creating a reflected data source. So we have a kind of reflection of the population of the sending side. And in this second simulator, it's possible then to use these spikes from the population in the sending application as part of the network in the second simulator. Music allows you to connect in loops, and these loops can be complicated. And as long as it's theoretically possible to ship data in that way, music will handle it. So it can actually be rather complicated, because you can imagine that if data on the needs to be available instantaneously, that is really an impossible problem, because theoretically, there will be some kind of delay. What you typically do if you have a numerical solver is that you use information from the previous time step to compute the present situation. And if you're communicating between simulators in loops, you will have to allow for some delay. So music allows time to shift relative to each other in different simulators. But the rule is that if you sum all of the delays over all connections in loops, this sum needs to be positive for it to be theoretically possible. So what you typically do is that if you have a neuronal population going between simulators, you tell music about the length of the connection delay, the size of the connection delay. You tell the music input port that it's acceptable to deliver spikes a little bit late, and you can sort of cover up this late delivery with a simulated connection delay. We won't go so much into those details here, but it's good to know that there is this concept of acceptable latency in music. You can tell music that it's okay to deliver a little bit late, but it's also okay from a modeling perspective, since you usually have delays on axonal projections. Okay, so typically, if you have parallel simulators, neuronal populations will be distributed over many processes. And of course, different simulators sometimes use different schemes for distributing neurons over processes. And this is one of the main problems that music helps you with. So a certain simulator informs music how neurons are distributed over ranks. And then music sort of can help with all of the complexity of moving data between the correct processes. And it actually does this fairly efficiently, because once you have told music about how neurons are distributed, these processes actually talk directly between each other. So there is no need to collect all of the spikes of all the simulation and then redistribute them, but it's done directly, and it's done in a scalable way. And of course, it wouldn't be possible to, at least for some types of data, it wouldn't be possible to collect it at one place because it would fill up memory. Okay. Yeah, I can skip that. Also, music allows different simulators to run with different step rates. So maybe you have one biologically detailed simulator that wants to run at a fairly detailed with detailed steps, like a tenth of a millisecond or something like that, and then you have a another simulator like Nest, where you might sometimes it might be enough with 1 millisecond. And you can sort of allow different applications using music to use different step rates, and music can coordinate how these talk to each other in a transparent way. The problem which then arises is actually more complex than you can imagine. So one could imagine that it would be sufficient to just sort communications between different applications in an appropriate manner, and that this will solve the general problem of how to communicate in this case. But that's not sufficient, because even with that kind of algorithms, you can end up, as shown in this picture, with situations where data now is dependent on data in the future. So the algorithm in music to solve how to communicate between applications, it needs to consider the entire connectivity graph between the applications in order to find a way to get data to the right place at the right time. Okay, so today we will look a little bit on different music interface. There is how to use music directly from a C++ application, how to use the music Python bindings, and also we will look a little bit of how you can use it from Pine. I also want to say that music has been used in research. So there is, for example, there has been a closed loop model of basal ganglia, spinal cord, and the body plant. There has been a model of action selection in a virtual robotic framework. And some tools have been using music as middleware. And currently, there is at least one larger project that is using music in HPP. Okay, so now for the tutorial. So has everybody who wants to have the Docker image, have you succeeded to download it? And have you succeeded to enter the environment, or do you have questions? So I wanted to start this tutorial by showing you the contents of the first directory in the Docker image, but I'm not succeeding to get a different font in Emacs. You normally do that by so okay, I'll stop screen sharing for a little moment. Okay. Okay, so let me share my screen again. So okay, so can you see my screen now?
Yes, and
Yes.
also read it.
Yeah, very good. Okay, so let's now look at a simple C++ application. So we want to write an application that sends a few spikes out through a music output port. So here we have it. So of course you have to start such an application by including the music header file. Here I create a class for spike events and a vector of spikes, where the first column here is time and the second one is identity of the neuron where the spike has occurred. So there are two phases when using music from an application. You have the setup phase where you configure music ports, and then you have the runtime phase where the communication actually happens. So we first create the music setup object in this line. And then we tell music that we want to have a port named out. And of course, you can have multiple output and input ports in an application. Then we inform music of what neurons exist on the current process. But in this tutorial, we will only use, at least in the beginning, one process. So we won't go into that complexity. So, but the principle is simply like in MPI, that different ranks give different ranges of indices to music. And there are different ways to do it. Here you give a range, a linear range of indices, but you can also specify them individually. It depends on what kind of distribution between ranks that simulators have. But now we simply say that, okay, we are responsible for 10 neurons, starting counting at neuron number 0. So what we do then is that we inform music about the existence of these neurons. And we do that by mapping the output port to these indices. So you can think of this mapping as a connection between the neurons and the port. Then we go into the second phase, the runtime phase of music. And here we have the basic simulation loop. So the conditions here is just that we want to make sure that we have spikes still left to send and that time has not passed 1 second. And for each of these spikes, we call insert event on the output port. And this sends the spike information through the output port. But the actual sending will actually only happen at certain intervals of time called the intertick interval. So you always run music with a certain step size, which we have informed music about here. And then we regularly call the tick operation, and that collects the spikes and sends them to the other side. And then we have to wrap everything up by calling finalize. So are there any questions about this? for some reason I don't. Björn, do you know when you're sharing screen, is it possible to have the chat window open in some way?
It may depend on your client, but yes, usually it is.
Because I don't see it. It's difficult for me to answer questions if you don't voice them. Yeah. Yeah.
So then people would need to just ask audibly.
Yeah, exactly. Okay. So this is how you send spikes using insert event on an output port. And then we look at how you receive spikes. Okay, so it's done in a similar way. You create a setup object, and here we publish the input port. And it's the same business with the indices. But the new thing here when receiving spikes is that you create a handler class, an event handler. And this handler will be called whenever a spike is received in the input port. So we have the simulation loop here, which is now empty, but actually when you leave control over to the music library in tick here, then the handler will be called for each received spike. So it's, even though this might look complicated, the design of music is done in a way that it should not demand a lot of work on an existing simulator to use it. Okay, so there is a make file here which shows how to build these applications. So we should be able to just type make now. Let me see if I can start an Emacs shell also. Okay, so I'll type make, and if you have downloaded this Docker environment, you should be able to do it you also. And I have no idea why that is so slow. Strange. Okay. So now we have these music-aware applications. And the final thing we need to do is to write a music configuration file. And this looks like this. So a music configuration file typically have different blocks, one for each application. So you have a sender application here, and this the name within these brackets is an arbitrary name that you can give to your application. So I've chosen to name this sender, and I've chosen to name the other one receiver. And here I specified what binary that music should launch for the sender, and also how many processes it should have if it's a parallel application. But in this case, it's a not a parallel application, and I just say that it wants one process. And then I connect the ports. I say that the output port named out in sender should be connected to the input port named in the receiver. And I also have to tell music what number of axons or data channels that should be expected in this connection. And then we should be able to run this simulation. So we then called MPI run, which is a part of OpenMPI. And I tell that we need two processes. It's one sender and one receiver. And music has a launcher called, it's a binary in itself, which reads the configuration file and then launches this simulation. So it's called spikes.music, the configuration file. And let's see what happens if I run it. Okay. So if we look at the receiver, I should have explained that. I didn't tell you what the handler did here. So what the handler at the receiving side does is that it prints the time and the spike identification on the terminal simply. That's what it does. And this is also what we get. So the spikes from the sender has arrived at the receiver and it works. So now I'll show you an advantage of using this kind of interfaces between applications. Is that it's now very easy to connect these applications to other applications. For example, the music distribution contains an event logger. It's essentially what Receive Spikes does now. It has an input port and it writes out the spikes on the terminal. But just to show you that we can replace this application, we will use event logger instead. So I just replace the binary and let's see what happens. And there you see the output from event logger instead. So the point here is that if you have music-aware applications, it's very easy to just reconfigure them and reuse them in different settings. So in a way, it's similar to this pipe sign in Unix. Okay, so that's everything I wanted to show you with regard to how to write a C++ application. So now is a good place for questions if you have it so far.
How did they do the synchronization, these two tasks? In this case, they have been started at the same time. So the timing that has been sent and the things that have been received, they started at about the same time.
Mm. Yes, that's a very good question. The answer is that music distinguishes different types of time. So, of course, we have the wall clock time, and your question refers to the wall clock time now. But usually, music instead looks at simulated time. So normally, if you run a neuronal simulation in a cluster, it's not simulated in wall clock time, but you have a simulated time that runs much slower. And in the case of music, we also have different simulators, each with its own simulated time. So what actually happens in this case is that music will be a little bit smart. So it realizes that it's not a good idea to send each spikes immediately because that would be inefficient. So what it instead does, it runs the first application for some time. And then it collects spikes. And once it decides now is a good point in time to ship a whole bundle of spikes, then it does that. So what actually happens in this example is that these simulations won't run simultaneously in wall clock time. they will run in their own simulated time, and relative to wall clock time, this will also be a bit shifted in order for music to be able to buffer spikes. All of these conditions can be sort of manipulated by giving information to music. Some adaptation will happen automatically. For example, if you connect two simulators in a loop, then of course music can't buffer a lot of spikes, but it needs to send them sufficiently fast not to in order to fulfill this acceptable latency condition that I talked about earlier. So the effect will be that as long as you have a chain of applications, music will probably run them shifted according to wall clock time. If you connect them instead in a loop, it will not buffer as much, but will communicate more often in order to shift the spikes around the loop. And in that case, the applications will run approximately, their simulated time will run approximately simultaneously according to wall clock time. And the synchronization, of course, music has a fixed communication schedule, and the synchronization between the simulators is then done through MPI. So the simulation at the receiving side will not continue until it has received the spikes that it should receive. That means that in this normal use case of music where you do not interact with real-time systems, then you can look at it as a deterministic simulation. So all spikes will arrive, and they will arrive in time according to what you have told music. You say that it's okay to deliver these spikes 10 milliseconds late, then you will receive all spikes in that time. So I hope that answered your question.
Thanks. Yes, I didn't. I am coming from this neuromorphic world where nothing is stoppable, and I didn't think of that you can synchronize them. Thank you.
Yeah.
Yes.
Yeah.
And okay, this is currently all done in, all the magic is in the tick.
Yes. Yeah.
Yeah. Thanks.
Mm-hmm. And what happens when you interact with a neuromorphic system is that you have a music-aware application which itself synchronizes its activity with wall clock time. And what will then happen is that the rest of the music system will automatically adapt to that, because it will sort of, as long as it can keep up with real time. But there is one of the papers I mentioned, this Vidal paper from 2016, discusses this and shows that, examples of systems where music runs in real time.
There's a question in the chat, but as you cannot see the chat, Mohammed, do you want to ask your question directly?
Yeah. Hi, Mikhail.
Hi.
So my question is about, you mentioned that in case of closed loop simulation, so it determines it doesn't buffer the spikes for long.
No.
So how does it determine the minimum delay time before sending the data, the exchange of data in between two different simulators, which expects the inputs at different time intervals?
Yeah. So if you have a projection between simulator A and simulator B, and in this projection there is a lot of axons, and you know that among these axons there is one axon with a very short delay. Let's say that the delay over that axon is 2 milliseconds. So what simulator B then does, because it's the simulator B which is responsible for modeling this projection, what it does is that it tells the music library that it's acceptable to deliver spikes into this input port 2 milliseconds late. That is what happens. So simulator B, the receiving application, will tell music that, okay, in this input port, it's okay to deliver the spikes 2 milliseconds late. And that means that if this particular neuron responsible for that axon, if it fires at time t, then music will at the latest have delivered that spike at time t plus 2 milliseconds at B. And that means that the simulation in simulator B still can cope with that event because it still has time to deliver it to its receiving neuron. So, of course, this complexity is usually not visible for the users because the simulator handles it. But in some cases, it's necessary to inform the music input port about this acceptable latency. And what you typically do then is that you set it to the same value as the shortest delay over a projection. Yeah. Okay. So let's now move to how it can look like when you use music from within a simulator. And I'll use the Nest simulator as an example. So let's now look at a Nest script which sends spikes. So I hope that many of you have seen Nest scripts before. You import a Nest module, and we create a spike generator and insert a few spike times there. And then we also create a neuron, and we connect the spike generator to this neuron. And we also create a voltmeter looking at the membrane potential of this neuron. And here comes the music specific part. So we first create the output port. Sorry, this is the Nest model name. So you need to be aware that what we are looking at now is how the Nest simulator developers have chosen to depict music output ports in their particular model description language. So this is a Nest model name. So music ports are called music event out proxy in the music simulation language, the Nest simulation language. We give this the name spikes out. And then we connect the spike generator to the music output port. So now we have kind of parallel flow of events. We have the origin of the spikes is the spike generator, and then we both ship it to a neuron which is local to this simulator. And then we also expose the spike generator spikes to a music output port. And then let's look at the receiving end. So here the model is called music event in proxy. That's how you sort of refer to music port in Nest, music input port in Nest. And then we do the thing similar to map in the C++ music script. We associate neurons with this input port. We again create a neuron N also here locally in the receiving simulator and print the membrane potential. So in the sending script, we have the spike generator connected both to a neuron and also to music output port. Here we have only a music input port which is connected to the neuron. So the idea here is that if we run this simulation, this co-simulation of these two Nest instances, then the spike generator spikes will both go to a neuron local to the sending side and also over the music ports to a neuron on the receiving side. And the idea here is that since both neurons on the sending and receiving side receive the same spikes, they will also behave similarly, and we will see the same membrane potentials from the voltmeter. So let's see also how the music configure script looks like. So we simply have a from application and a to application, and the from is this nest script, which we looked at first, and then the second receive nest script. And we simply connect the spikes out port to the spikes in port. And now we should be able to run those two nest instances together. Was it called nest.music? Okay. So we have the music launch application and then the configure file. Okay, it worked. So presumably what we're seeing here first is the membrane potentials of the local neuron on the sending side, and then we see here the membrane potentials of the neuron on the receiving side. That worked. So any questions on this?
When you're using nest here, this I'm always thinking collaboratory as well, but that's probably then not possible to do that over there. So if I would, in the Pine tutorial, we saw a nest running in a process in the lab, in the eBrain's research infrastructure lab, and as you mentioned Pine music already. Could that work?
Yes, I mean, absolutely. It's just that that is not entirely finished, that integration.
Okay. Yeah. So there will be. Thank you. Yes.
Yeah, yes. Right. Okay. So this is also the reason why I provided this Docker container, such that I hope that those of you who are interested will actually download the container and play around a little bit with this. Because what you can do, of course, is also to change a little bit in the parameters and yeah, try out different configurations. Okay, so let's now look at how the Python bindings of music look like. And we'll see first the archetypical send application. This is simply the Python mirror of the C++ send spikes application. So here you import the music module. And what I make here is an iterator iterating over a set of spikes, which I in Python model as tuples. So as usual, we create a music setup object. We publish the output port. We do the mapping, telling music what neurons we are responsible for. Then we enter the runtime phase. And here is a simulation loop. And it's actually, it's nothing special here. We simply have a loop calling tick, which music will make sure is done regularly in simulated time in local simulated time. And for each of these time intervals, the inter-tick intervals, we have a loop pushing out all relevant spikes. I should say that it's actually possible to just ship out all of the spikes in the first time step. That's possible. Music will handle it and handle it appropriately for receivers. But it's cleaner and more scalable to do it this way, to handle even at the sender, to ship out just the relevant spikes for this interval. And let's see how the receiving end looks like. Yeah, similarly to the C++ case, we define a handler. This is a strange argument which you can ignore here. It has something to do with, so music can actually handle different types of neuron identity. You can enumerate the neurons locally in a local process, or you can handle instead the identities taken across the entire simulation over multiple processes, but we don't go into that complexity here. So we have a spike handler, which becomes called inside the tick call here. So here's the simulation loop. And what we do in the handle, as in the C++ application, is simply to print the incoming spikes on the terminal. And maybe we should look also at the music configuration file. Nothing strange there. It's just that it's now Python scripts. Okay, so let's start that. And as expected, the receive spikes script prints out the spikes that it has received. In this directory, I also have an example of a nest model which is connected to a Python script in a loop. Maybe we can look at the configuration file. So I have a nest application with this nest model in it. And we have our Python script, and I tell them that the spikes output port of the nest model should be connected to the in port of the script, and the out port of the script should be connected to the in port of the nest model. And here is the nest model, which both creates the input port. We don't need to look at the details here. And also an output port down here. And then we connect both to this parrot neuron, apparently. Yes. So what we do in the script is that we, in the event handler, we receive an incoming spike, and then we send it back to nest 0.2 of a second later. 200 milliseconds later, right? So it's like a ping pong situation, that we have a spike that goes around between these applications, just to demonstrate the loop. So let's see here. Is it called roundtrip.music? Okay. So there is a spike in the first application that comes to the to the script, and then is sent back 200 milliseconds later, and then it's sent out again, and so it continues. Okay. So, and of course you can use this as a template if you want to try out this on your own model or some more serious application. And of course, it's you are always welcome to ask me questions over email, and I will try to help you. Okay, so now the Pine music interface. So, of course, when designing the music interface and the Python binding, the aim was to make this fairly easy to use, but the problem is in its nature a little bit complicated. And what is very good with APIs that we have talked about is that you can abstract over complexity and try not to get involved with the complexity. And of course, if you're a Pine user, it would be very nice if you didn't have to bother about creating music output and input ports. Maybe you could just specify what simulators you want to use. So here is a Pine script where we load the music module of Pine, because this is the Pine music interface. So what you do here is simply to say that I want one process of Nest and I want one process of Neuron. And then we can create, so here, Sim1 here, I could have named them Nest and Neuron, of course. Sim1, which is Nest, we set up both as you usually would in a Pine script. And then what we can do is to create a population in the Nest simulator by using the Nest simulator handle there. And similarly, we can create a population in Neuron this way by using the Neuron simulator handle. And then we simply create a music projection going across these simulators. And you only have to mention the variables for the populations on the Nest and Neuron sides. And the Pine music interface will cover all of the other complexity. And then we call music run to launch the simulation. And we have to call music end at the end. So the other stuff in this simulation you should recognize if you're familiar to Pine. So it's as simple as that. So you sort of create the different simulator instances. You have handles to them, and you can use the handles to create populations on either side. And then you use a music projection to to set up the projection across. And let's see if this works. Yeah, what does we didn't talk about what the script does. So what it does is that it records the spikes on the receiving side, and we compute the mean firing rate. And what do we have? We have 20 sending neurons, and we have 4 receiving neurons on the other side. And we have a random connection, fixed probability connector with the 50% probability between this. So it's full connectivity diluted with this randomness. Okay, so let's run that. Now we don't use the music launcher, but we instead use Python as usual when you run Pine scripts. Okay, so we got a mean firing rate of 0.25 Hertz. And just now, to show you that we are actually running this simulation, we can maybe increase the probability and see what happens. Oops. And we got a higher firing rate. We can do fun things, like maybe we want to let's say that this had been really large simulations. Then maybe we would have wanted to use multiple processes on a cluster, so we can have 2 instances of Nest and 2 instances of Neuron to do this. And then, of course, we need to give the simulation 4 ranks. So we have 2 nests, and it's still the same result. And one final thing, maybe. So maybe we want the sending simulator to be Neuron, and the receiving simulator to be Nest. I changed the number of processes, right? So it should be 2 here. Okay, and we have the same results. So now it was Neuron that sent spikes to Nest instead. Any questions on that?
You mentioned you started with C++, that maybe due to people who want to write music interfaces to their own simulators? Or what would be the disadvantage to use the Pine way that you just showed?
Yeah, no, I mean, of course, if you can use the Pine way, that is simple and good. But in this case, the reason why it works is that Nest and Neuron have Pine backends. But it could be that you want to use a simulator that doesn't have a Pine backend. I should say also that it does not only need a Nest and Neuron backend, but these backends must have the support for the Pine music interface. And in many cases, you need some other completely different application, which is not supported by Pine, or maybe you want to write some very efficient application doing some processing of the spikes. That are examples when you won't use this.
And it can, of course, be mixed. So I can use Nest and Neuron with PineNest, with the music Pine interface, and let them talk to something that has been written specifically, as you mentioned.
Yeah, this is intended to be possible, but I think that there is a part of the Pine music interface which allows you to talk to external music-aware applications. That part is currently broken. I will fix it. So yeah, and this is also this. I should mention that the software which I've now demonstrated is not the standard releases, but they are in different branches of the Pine and Neuron repositories currently. But I'm working with the developers to include this in the main branch as soon as possible. So maybe I could. I of course have a Docker configuration script for the environment that is used in this lab. So if people really want to have access to the software which supports this, they can contact me, and I will. But otherwise, it will soon be in the main releases. And also the part of the Pine music interface that talks to external devices, I will need to fix that simply. Yeah. Okay. So that was the demonstration of the different interfaces to music. So are you ready now for an example of music talking to Spinnaker?
At least I'm interested.
Okay. So then I will try to find.
And even as you might not see this, there's at least another thumbs up in the Zoom.
Okay, I don't see that. Yeah. So should I answer a question?
No. I just mentioned there was another thumbs up to your question, whether there is now interest in the.
Okay. Okay. Sorry. Yeah. I'm running the presentation in a virtual machine. Okay. So then I think I will only. How do you do this? Like that. Okay, so what you will see, or hopefully see if this works, here is actually a whole set of music applications working together. So the image here is depicting the ROS music toolchain that was published in the Weidel 2016 paper. And the only difference now is that in that paper, the neural network was simulated in Nest. But since we know all of these are music-aware applications, what I did was that I replaced this portion, the neural simulator portion, with a Spinnaker model running in Spinnaker, and then I put at these arrows, I sort of added something called, which I've written, which is called music Spinnaker adapter. So we have one output adapter and one input adapter. So one application which can receive music spikes and can send them via UDP to Spinnaker, and then another application which can receive spikes via UDP from Spinnaker and put them into the music world. And then it was possible to simply reuse the other parts of the toolchain just by changing the music script. So maybe we should, I should explain a little bit of what parts are in this toolchain. So the idea here is to model something called a simple Breitenberg vehicle. So you have a very simple brain consisting of two neurons in this case. So you have one neuron which is driving one side of a little wheeled robot, and then the other neuron driving the other side. And this has a laser scanner, and there is a simple neural network between the scanner input and the neurons. So the idea is simply that if you have an obstacle on one side, the scanner will see it, and that will push up firing rate on the neuron on that side, which will push the wheels on that side, and it will steer away. So I should say that I had little trouble when preparing this because it seems like in the newer versions of ROS, they have changed probably something in the numeric values for this scanner. So it does not work as well as previously, but I hope you will see that it reacts at least to the environment. So the robot is simulated using ROS and the gazebo simulation framework, which also NRP uses, by the way. So we have the robot simulated in gazebo and in the ROS framework. And then there are ROS music adapters, which are applications that connect the ROS robot operating system world with the music world. And so you have the laser scanner in the robot, and the input from the laser scanner is transformed by adapters in the music world, which convert them to spike trains, and then the spike trains are fed into this Spinnaker music adapter, which sends the spikes to Spinnaker. And then something similar happens the other way, that the spike trains from Spinnaker are decoded into continuous data, also sent through music. And this continuous data is driving the wheels of the robot. So there are many steps here. So it's actually 4 applications before you talk to the ROS world on one of the chains, and then 4 applications on the other. So let me see if I can start this. Let's try again sharing the screen. Okay, now you can see the Pine Music window, or?
Yes, I can
Yes,
see the
okay.
Pine Music window.
So what I'll do now is to launch the simulation and move in the gazebo window to the screen. Let's see if that works.
Aha.
Can you see it?
Incoming is a window with an environment. Yes.
Yes. Okay, so now here is the robot, and there's obstacles, and here's the lasers, and there's everything. And then now the imaging is in the car. Now.
Wow. Currently we have a really chopped off audio, as if your machine is at the limit.
Yes. Let's try again.
Your audio is back to normal.
Yeah. Let's try again. So maybe there is a problem running this together with Zoom. So let's try once more, and I'll be quiet.
Should we see anything happening?
Yeah. Yeah. Unfortunately, it seems like it's. Yeah. Can you hear me now?
Yes, I can.
Yeah. What is happening is that the capacity is not enough for this computer to both run the Zoom meeting and
the simulation
simulator and the Spinnaker interfaces. And I mean, yeah. So I tested this before the meeting, of course, and then it worked. But yeah. So unfortunately, maybe, yeah. I think we should not try something else right now.
Probably not.
No. Right. Okay. So then we should wrap it up.